Jupiter was killing things before we even got close enough to look. Not metaphorically, not as a figure of speech. The first probe that approached close enough to take real measurements absorbed a radiation dose roughly 1,000 times the lethal human threshold in just a few hours. The spacecraft survived, barely. A human being would have been dead before the data started coming in. And that was just the outer edge, just the suburbs of what Jupiter considers its personal space. We look at it through telescopes and we see something almost peaceful. Pale orange bands layered over creamy white. That enormous red oval sitting in the southern hemisphere like a decorative feature, something that belongs on the wall of a science classroom, slightly majestic, slightly distant, fundamentally unthreatening. The kind of planet that shows up in the background of science fiction films to make a scene look cosmic and beautiful. That picture is wrong in almost every way that matters. Jupiter is not a big version of a normal planet. It is not Earth scaled up. It is not something familiar operating at an unfamiliar size. It is a fundamentally different category of object, something that operates by rules that have almost nothing in common with the rules that govern the world you are standing on right now. And the gap between what it looks like from here and what it actually is, physically, mathematically, in terms of what it does to everything around it, is one of the largest gaps between appearance and reality in the entire solar system. By the time this is over, you are going to understand why planetary scientists sometimes describe Jupiter not as a planet with moons, but as a failed star with a solar system of its own. Why the radiation environment around it is comparable in some ways to the interior of a nuclear reactor. Why the storm system we have been watching for over 350 years is an engine of violence operating at a scale that makes every weather event in Earth's recorded history look like a light drizzle. Why Jupiter may have saved every living thing on this planet multiple times over, and may also be responsible for some of the most catastrophic mass extinction events in Earth's geological record. Both of those things, the same object, simultaneously. Start with the size, because the size is where the strangeness begins and where most people's mental models immediately break down. Jupiter has a diameter of approximately 140,000 kilometers. Earth's diameter is about 12,700 kilometers, so Jupiter is roughly 11 times wider than Earth. That sounds like a big number, but it still feels manageable. 11 times, okay, like 11 Earths lined up side by side. But diameter is not the right measurement for understanding the difference. Volume is. And volume scales with the cube of the diameter. 11 cubed is 1,331. You could fit approximately 1,300 Earths inside Jupiter's volume. Not lined up, packed inside. 1,300 of them. That number is already difficult to hold in your head, but it gets stranger. Jupiter's mass is roughly 318 times Earth's mass, which means that if you took all 1,300 Earths you just packed inside Jupiter's volume, they would still only account for about 4 times Jupiter's actual mass. Jupiter is not just large, it is extraordinarily dense relative to its size, in a way that tells you it is made of something fundamentally different from rock and iron. It is made primarily of hydrogen and helium, the two lightest elements in the universe, and yet it outmasses Earth by a factor of 318. The reason is pressure. At the depths where Jupiter's atmosphere transitions into something that can no longer really be called an atmosphere, the pressure is so extreme that hydrogen, the lightest gas in the universe, the stuff that makes balloons float, stops behaving like a gas. It stops behaving like a liquid. It enters a state that does not exist anywhere on Earth and cannot be recreated in any laboratory on Earth with current technology. It becomes metallic hydrogen, a phase of matter in which hydrogen atoms are compressed so tightly that their electrons stop belonging to individual atoms and instead flow freely through the material, the way electrons flow through copper wire. Metallic hydrogen is electrically conductive, and because Jupiter is rotating, completing one full rotation in just under 10 hours, faster than any other planet in the solar system despite being the largest, that rotating shell of electrically conductive metallic hydrogen generates a magnetic field. Not a magnetic field like Earth's. Earth's magnetic field is strong enough to deflect compass needles and protect the surface from solar wind. Jupiter's magnetic field is approximately 20,000 times stronger than Earth's. It is the strongest planetary magnetic field in the solar system. It extends outward from Jupiter for millions of kilometers in every direction, creating a magnetosphere so vast that if it were visible to the naked eye from Earth, it would appear larger than the full moon in our sky, even though Jupiter itself is just a bright point of light. And inside that magnetic field, trapped and accelerated by it, are charged particles moving at velocities approaching the speed of light. Protons, electrons, ions of sulfur and oxygen, all of them spiraling along magnetic field lines, gaining energy, colliding with each other, and with anything unfortunate enough to be orbiting in the wrong place. This is the radiation environment that killed the first probe in hours. This is why every spacecraft NASA has ever sent to orbit Jupiter has had to be armoured with radiation shielding that adds hundreds of kilograms of mass to the vehicle. This is why the Juno spacecraft, which arrived at Jupiter in 2016 and has been orbiting it ever since, was designed with its most sensitive electronics housed inside a titanium vault, specifically to protect them from a radiation environment that would otherwise destroy the instruments within weeks. Juno has now completed dozens of orbits of Jupiter. Engineers estimate the spacecraft has absorbed a radiation dose equivalent to over 100 million dental X-rays. It is still functioning. It is a remarkable piece of engineering. But every orbit degrades it slightly further, and the mission will eventually end not because the spacecraft runs out of fuel or because ground controllers decide to end it, but because the radiation will eventually overwhelm even a titanium vault. Now hold that thought, the radiation, the magnetic field, the metallic hydrogen, and look at the atmosphere above it. Because the atmosphere is where Jupiter performs its most visually dramatic violence. And it is also where some of the most genuinely strange physics in the solar system is happening right now, continuously, without pause. The bands you see on Jupiter, those pale orange and white stripes, are the tops of cloud systems moving in opposite directions at hundreds of kilometers per hour. The light-coloured bands are called zones. The darker bands are called belts. Zones are regions where gas is rising from deeper in the atmosphere, cooling as it rises, and flowing outward laterally at the top of the cloud layer. Belts are regions where gas is sinking back down, warming as it descends. The entire visible surface of Jupiter is a system of counter-rotating atmospheric rivers, each one spanning the full circumference of the planet, each one moving at wind speeds that would classify as beyond any category on Earth's hurricane scale. Wind speeds in Jupiter's atmosphere regularly exceed 500 kilometers per hour in the jet streams between the bands. For reference, The strongest wind ever recorded on Earth's surface was approximately 408 kilometers per hour during tropical cyclone Olivia in 1996. That was a record, an extraordinary outlier. On Jupiter, winds that fast are not a record. They are background conditions. They are the calm regions between the more violent structures. Between those counter-rotating bands, at the boundaries where zones meet belts, the wind shear, the difference in velocity between adjacent flows, is so extreme that it generates turbulence that cascades down through scale after scale. Large eddies break into smaller eddies, which break into smaller ones, which break into even smaller ones, all the way down to structures too small for our instruments to resolve from Earth. The entire visible atmosphere of Jupiter is in a state of turbulent cascade that has been continuous for as long as we have been watching, and almost certainly for billions of years before we started. Lightning happens inside those clouds constantly, not occasionally, constantly. Jupiter's lightning was first detected by the Voyager spacecraft in 1979, and what the instruments found surprised everyone. The lightning was occurring at rates orders of magnitude higher than on Earth. Later measurements from the Juno spacecraft, which carries instruments specifically designed to detect lightning radio signals, confirmed that Jupiter experiences roughly 6 lightning strikes per square kilometre per year in its most active regions. Earth experiences roughly 1. And Jupiter's individual lightning bolts are fundamentally different from Earth's. Not just bigger, but different in the type of electromagnetic emission they produce, concentrated in frequencies that suggested the discharges were happening in a part of the atmosphere where water clouds form, deep beneath the visible ammonia cloud layer, in conditions of pressure and temperature that have no equivalent anywhere on the surface of Earth. The reason there is water down there, and there is water in substantial quantities, matters for understanding what Jupiter actually is physically. Jupiter formed from the same material as the early solar system, the same cloud of gas and dust that also formed the Sun. When the Sun ignited and began radiating energy outward, the light and heat blew most of the light gas, hydrogen, helium, away from the inner solar system. Rocky planets formed from what was left closer to the Sun. Jupiter formed far enough out that it captured an enormous envelope of that primordial hydrogen and helium before the Sun could disperse it, and it grew massive enough that its gravity held on to everything else as well. Water vapor, ammonia, methane, traces of every compound that existed in the early solar nebula. So the deep atmosphere of Jupiter is not just hydrogen and helium, it is a primordial chemical archive, a sample of the original material of the solar system, compressed and heated and stirred for 4.5 billion years, but still containing molecular signatures of what the solar system was made of before anything else formed. When scientists analyze the composition of Jupiter's atmosphere, they are in a very real sense reading the chemical autobiography of the solar system. They are looking at the ingredients that were available when the planets formed, preserved in the largest natural container in the solar neighborhood. And that composition has surprises. Jupiter contains more heavy elements relative to hydrogen than the Sun does. More carbon, more nitrogen, more oxygen, more sulfur. The enrichment is significant enough that it cannot be explained simply by Jupiter forming from solar composition material. Something added extra heavy elements. The leading hypothesis is that during Jupiter's formation, it was bombarded by enormous numbers of planetesimals, the rocky and icy building blocks that were assembling into planets throughout the early solar system. and those impacts delivered heavy elements into Jupiter's forming atmosphere in quantities large enough to measurably enrich it above solar composition. This means Jupiter may have consumed a substantial fraction of the early solar system's solid material. Rocky bodies, icy bodies, the precursors to what might have become additional planets, all of them falling into the growing giant and being dissolved into its atmosphere. Jupiter did not just form, Jupiter consumed. It grew by eating the solar system around it, and the chemical record of that consumption is still preserved in its atmosphere today, waiting to be read by spacecraft with instruments sensitive enough to detect the signatures. The Galileo probe read some of those signatures in 1995. It was the first, and so far only, spacecraft to actually enter Jupiter's atmosphere. It descended on a parachute for just under an hour, transmitting data as it fell through layers of cloud and increasing pressure and temperature, before the pressure crushed it and the heat melted it, and it was swallowed entirely. In that 1 hour of data, it detected winds of over 500 kilometers per hour. It found that the lightning in the deeper atmosphere was far more intense than surface measurements had suggested. It found that some of the elemental abundances were different from what models predicted, which required significant revisions to theories of how Jupiter formed. It also found something unexpected about the water. Models predicted that the Galileo probe's entry region should contain substantial water vapor, because the chemistry and physics suggested water clouds should form at that altitude and latitude. The probe found much less water than expected. This confused scientists for years. The eventual explanation, supported by later Juno data, is that the probe happened to enter through what is called a hotspot, a relatively dry, cloud-free region where unusual circulation was pulling atmospheric gases down from high altitudes, depressing the water content locally. The probe was unlucky in its sampling location, or perhaps the planet was performing a kind of trick, showing the spacecraft an atmospheric region that was unrepresentative of Jupiter as a whole. This is something Jupiter does repeatedly when we look at it. The thing that is visible is not the thing that is representative. The surface tells lies about the interior. The calm-looking bands contain violence. The beautiful oval tells nothing about the depth. The oval. The Great Red Spot has been observed continuously since the 1660s, when astronomers first documented a persistent oval storm feature in Jupiter's southern hemisphere. That is 360 years of continuous observation of a single storm, the longest running storm ever documented on any planet. It was significantly larger when first observed. Historical measurements suggest it was once large enough that 3 Earths could fit inside it, side by side. Today, it is roughly the size of 1 Earth. Still an incomprehensibly large storm, but smaller than it used to be, and the rate of shrinkage has been accelerating. This is one of the genuinely unsettled scientific questions about Jupiter right now. The Great Red Spot is shrinking and changing shape. In the early 20th century, it was still roughly twice the diameter of Earth. By the 1970s, Voyager imagery showed it had reduced to about 1.5 Earth diameters. Observations through the 1980s and 90s showed continued shrinkage. Recent measurements from Juno and from Hubble show the storm currently measuring roughly 1.5 times Earth's diameter, significantly smaller than historical observations, and displaying an increasingly circular shape compared to the elongated oval it maintained for centuries. The mechanism of the shrinkage is not fully understood. One hypothesis is that the storm is simply running out of energy, that the temperature differential between Jupiter's interior heat and its upper atmosphere that drives the convection powering the storm is slowly being equilibrated. Another hypothesis is that the storm is being eroded by smaller vortices around it, consumed by the same kind of turbulence it generates. Juno data has revealed that the Great Red Spot extends far deeper into Jupiter's atmosphere than previously thought, perhaps 300 kilometers below the visible cloud tops, which complicates simple models of how the storm maintains itself and how it could lose that structure. Some researchers have proposed that the storm might eventually break apart entirely, that within decades or centuries, the most prominent feature on the largest planet in the solar system, a storm that has outlasted every human civilization of the last 3 centuries, that was already ancient when the American Revolution happened, that was spinning when Newton was writing the Principia, might simply stop, dissolve into the surrounding atmosphere, leave nothing but another turbulent boundary between adjacent jet streams. Whether that happens or not, and on what timescale, is genuinely unknown. Jupiter's atmosphere operates on timescales that dwarf human observation records. 360 years of watching one storm is, in the context of Jupiter's 4.5 billion year history, equivalent to watching a human being for approximately 2 milliseconds, and concluding you understand their behavior. We have caught a glimpse. We have no idea what the full story is. What we do know is what powers the storm at the level of basic physics. The Great Red Spot is an anticyclone, a high-pressure system rotating counterclockwise in Jupiter's southern hemisphere. On Earth, high-pressure systems are associated with clear, calm weather, precisely because they suppress the vertical atmospheric motion that creates clouds and storms. On Jupiter, the same basic dynamics produce something radically different, because Jupiter's atmosphere is not bounded below by a solid surface. On Earth, atmospheric systems interact with the ground. Friction with the surface dissipates energy. Mountains disrupt airflow. The ocean absorbs and releases heat in ways that modulate storm intensity. Jupiter has no surface in any meaningful sense. The atmosphere simply gets denser and hotter as you go deeper, transitioning gradually from gas to liquid to the metallic hydrogen phase, without any sharp boundary, without any solid ground to interact with. An atmospheric vortex on Jupiter can extend vertically for hundreds of kilometers without ever encountering anything that would disrupt it. It can draw energy from the internal heat flowing upward from Jupiter's deep interior. Heat left over from the planet's formation 4.5 billion years ago, still leaking outward, still driving atmospheric circulation that has been continuous since before Earth existed. Jupiter radiates more energy into space than it receives from the Sun. This is not a small effect. Jupiter emits roughly 1.7 times as much energy as it absorbs from sunlight. The excess comes from that primordial heat, the gravitational energy of formation, still slowly being released, still warming the planet from within. Jupiter is cooling down, but it is doing so on a timescale of billions of years, and in the meantime, the outward heat flux drives convection throughout its atmosphere, providing an internal energy source for weather systems that has no equivalent on any rocky planet in the solar system. This internal heating is why Jupiter's equatorial temperature at cloud top level is roughly similar to its polar temperature, despite the poles receiving far less sunlight than the equator. On Earth, the poles are dramatically colder than the equator because Earth's climate is predominantly driven by sunlight, which is much weaker at the poles. Jupiter's climate is predominantly driven by its internal heat, which is symmetric and global, producing a much more uniform temperature distribution at the cloud tops. The storms at Jupiter's poles, which Juno photographed for the first time in detail in 2017, are enormous cyclonic systems arranged in geometric patterns, 8 around the North Pole and 5 around the South Pole, each one large enough to contain multiple Earths, all of them persisting for years of observation without merging or dissipating, held in their geometric arrangement by forces that are still being studied and modelled.
Those polar cyclones are unlike anything on Earth, and unlike anything in previous models of planetary atmospheric dynamics. The fact that they arrange themselves in stable geometric configurations, an octagon of storms around the North Pole, a pentagon around the South, rather than merging into a single polar vortex as models predicted, suggests there are dynamical constraints operating in Jupiter's polar atmosphere that current physics does not fully explain. Juno has observed them continuously for years. They have not merged.
They have not dissipated. They rotate slowly around the poles in their geometric formations, stable as crystals, violent as hurricanes, arranged with a mathematical precision that seems almost too neat for a system driven by turbulent fluid dynamics. And then there are the moons. 67 confirmed major moons and numerous smaller captured objects. 4 of them, Io, Europa, Ganymede and Callisto, are worlds in their own right, each one large enough that if it orbited the Sun directly rather than Jupiter, it would be classified as a planet without hesitation. Ganymede is larger than the planet Mercury. It has its own magnetic field, generated by its own liquid iron core, making it the only moon in the solar system known to generate its own magnetosphere. It orbits inside Jupiter's magnetosphere while generating a smaller one of its own, a magnetic bubble inside a magnetic bubble, creating complex interactions between the two fields that produce aurora on Ganymede, visible to spacecraft instruments. But Io is where Jupiter's violence becomes most direct, most visible, most undeniable. Io is the innermost of the 4 large moons. It orbits Jupiter at a distance of roughly 420,000 kilometers, closer than our moon orbits Earth. At that distance, Jupiter's tidal gravity does not merely raise ocean tides the way the moon raises tides on Earth. Io has no ocean. The tidal force flexes the rock itself. The entire moon is squeezed and stretched by Jupiter's gravity, and by the gravitational resonance with the other large moons, which pull Io's orbit slightly out of the circular path that would minimize tidal stress, in a cycle that repeats every 42 hours as Io completes one orbit. Squeezing and stretching rock generates heat through friction. The heat generated by tidal flexing in Io's interior is enormous, roughly 2 watts per square meter of surface area, averaged across the entire moon. Earth's internal heat, by comparison, generates roughly 0.09 watts per square meter. Io generates heat internally at a rate roughly 20 times higher than Earth does per unit of surface area, and Io is significantly smaller than Earth. The total internal heat generation rate on Io is approximately 2.5 times 10 to the 13th watts, greater than the total heat generated by radioactive decay throughout Earth's interior. That heat has to go somewhere. It goes into volcanoes. Io is the most volcanically active body in the solar system. Not historically, not in some past geological era. Right now, currently. As of the last observations taken before this was written, Io has over 400 identified volcanic structures on its surface. During the Voyager flybys in 1979, 9 active volcanic plumes were observed simultaneously. Subsequent observations by the Galileo spacecraft, by Earth-based telescopes, and by the New Horizons spacecraft during its Jupiter flyby in 2007 have documented eruptions continuously. Some of Io's volcanoes are enormous, in a way that requires numbers to appreciate. The Loki Patera is a volcanic depression, a lava lake, covering an area of over 20,000 square kilometers. That is larger than the area of the state of New Jersey. It is filled with molten silicate lava. It periodically brightens, meaning the lava overturns, bringing fresh, hot material to the surface, on a cycle of roughly 500 days that has been documented for decades and that may be regular enough to be predicted. How a volcanic system operates on a 500-day cycle on a moon whose internal heat is generated by a gravity gradient has been debated extensively. One model suggests the Loki Patera lava lake overturns because a wave of solidified crust gradually thickens around the edges until it becomes dense enough to sink, triggering a resurfacing event that propagates around the lake like a wave, a process called overturn, similar in some ways to the overturning of a lava lake on Earth, but operating on a vastly larger scale and longer timescale. The plumes erupting from Io's surface reach heights that dwarf anything on Earth. The Pele volcano, named for the Hawaiian goddess of fire, produces a plume that reaches approximately 300 kilometers above the surface. Earth's largest volcanic eruptions reach maybe 40 kilometers into the stratosphere under exceptional conditions. Io does 300 kilometers, continuously. The material ejected from Pele contains sulfur dioxide and sulfur compounds that condense at altitude and rain back down onto the surface, creating a ring of reddish, sulfurous deposits around the vent, visible from spacecraft imaging, that spans an area larger than the continental United States. Io's surface is continuously resurfaced by this volcanic activity. The bombardment rate of meteorite impacts throughout the solar system should have left Io's surface covered with craters, the way the Moon is covered with craters, the way Mercury is covered with craters, the way the surfaces of countless other bodies in the solar system are covered with craters. Io has almost no craters. The ones that form are buried within centuries under new volcanic deposits. The entire surface is geologically young, perpetually renewed. The oldest exposed terrain on Io perhaps only a few million years old in a solar system that is 4.5 billion years old. And this volcanic activity has a direct connection to Jupiter's radiation environment. The material erupted from Io's volcanoes, sulfur dioxide, sulfur, oxygen, sodium, escapes into space and is ionized by radiation and UV light. The ionized particles are captured by Jupiter's magnetic field. They form a torus, a donut-shaped ring of plasma, orbiting Jupiter at roughly the same distance as Io's orbit. This Io plasma torus contains roughly 1 metric ton of new material per second, continuously added by Io's volcanism, continuously processed by Jupiter's magnetic field. The torus is one of the densest concentrations of plasma in the solar system outside of the Sun itself. It glows in ultraviolet light. It emits radio waves that can be detected from Earth. It contributes charged particles to the radiation belts that make the inner Jovian system so lethal. So the radiation that nearly killed the first probe approaching Jupiter is, in part, powered by Io's volcanoes, which are powered by tidal heating, which is powered by Jupiter's gravity. Jupiter is generating its own radiation field by gravitationally squeezing its innermost large moon into a volcanic furnace that constantly feeds plasma into the magnetic trap. The planet is manufacturing its own danger. Europa is the next large moon outward from Io. It is roughly the size of Earth's moon. From a distance, it looks pale and smooth, a whitish sphere covered with long linear markings and very few craters. It is one of the smoothest large bodies in the solar system. The reason for the smoothness is the same reason for the linear markings, and both things point to the same conclusion that has been making planetary scientists increasingly excited for decades. Europa's surface is water ice. Not a thin coating of frost. A global shell of water ice, estimated to be between 10 and 30 kilometers thick, covering the entire moon. Beneath that ice shell, models and measurements both strongly suggest is a liquid water ocean. A global ocean of liquid water, kept liquid not by proximity to the sun — Europa is far too cold for that — but by tidal heating from Jupiter's gravity, the same mechanism that powers Io's volcanoes, but operating more gently at Europa's greater distance, generating enough heat to maintain liquid water beneath the ice, but not enough to tear the moon apart. The evidence for this ocean has accumulated over decades. The linear markings on Europa's surface are fractures in the ice, places where the ice shell cracked and shifted and refroze, analogous in some ways to sea ice on Earth's Arctic Ocean. The scarcity of craters indicates the surface is young, constantly renewed by geological activity driven by the ocean-ice interaction below. The Galileo spacecraft measured perturbations in Europa's magnetic field that are best explained by the presence of a conducting layer, a salty liquid ocean, beneath the ice. The Hubble Space Telescope has detected what appear to be water vapor plumes erupting from Europa's surface in some locations, analogous to the geysers on Saturn's moon Enceladus, suggesting that at least in some places the ocean is communicating with the surface. If the ocean exists, and the evidence is strong enough that most planetary scientists now treat its existence as likely rather than speculative, it contains more liquid water than all of Earth's oceans combined. A global ocean, in contact with a rocky sea floor where the tidal heating from Jupiter may be powering hydrothermal activity similar to the hydrothermal vents on Earth's ocean floor. The hydrothermal vents on Earth's ocean floor support rich ecosystems that derive energy from chemical reactions rather than from sunlight. They were discovered in 1977 and were immediately recognized as evidence that life does not require sunlight. It requires only liquid water, chemical energy, and the right molecular building blocks. Europa may have all three. Liquid water, chemical energy from tidal heating and potential hydrothermal activity, organic molecules delivered by the constant meteorite bombardment that the outer solar system experiences. The question of whether Europa's ocean harbours life is one of the most significant open questions in planetary science. It is significant enough that NASA has funded and is currently developing a mission called the Europa Clipper, launched in October 2024, designed to fly past Europa dozens of times and characterize its ocean, its ice shell, and its surface in detail sufficient to assess its habitability. The Clipper is not a life detection mission. It will not be able to confirm or deny whether life exists in Europa's ocean. But it will tell us whether the conditions for life are present, which is the necessary first step before more capable future missions can attempt to answer the harder question. This is where Jupiter's story becomes philosophically strange in a way that goes beyond physics and chemistry. Jupiter is simultaneously the most dangerous environment in the solar system for anything resembling life as we know it. The radiation belts, the extreme magnetic field, the crushing pressures and temperatures, and potentially the host of the most significant reservoir of liquid water in the solar system, possibly harbouring a biosphere that has had 4.5 billion years to develop in isolation from the rest of the universe. The same planet, the same gravitational field that generates the lethal radiation, also maintains the tidal heating that keeps Europa's ocean liquid. The destroyer and the life-giver are the same mechanism, the same force. This is not the only paradox in Jupiter's relationship with life. Consider what Jupiter does to the inner solar system, to the region where Earth sits and where life has actually developed. Jupiter is massive enough that its gravitational influence reaches throughout the solar system. Its gravity perturbs the orbits of smaller bodies, asteroids, comets, in ways that can either send those bodies toward the inner solar system or deflect them away from it. For decades, the dominant hypothesis in planetary science was that Jupiter acts primarily as a shield, its gravity capturing or deflecting comets and asteroids that might otherwise impact Earth, reducing the bombardment rate in the inner solar system and giving life on Earth a more stable environment in which to develop. The Jupiter shield hypothesis was influential. It appeared in textbooks. It was part of the standard story about why Earth is habitable. Then the models got better. More detailed simulations of Jupiter's gravitational influence on the early solar system produced a more complicated and more unsettling picture. Yes, Jupiter deflects some comets away from the inner solar system, but Jupiter also perturbs the orbits of bodies in the asteroid belt, the region between Mars and Jupiter, in ways that can send asteroids into Earth-crossing orbits. The same gravitational resonances that cleared gaps in the asteroid belt also periodically pump asteroids out of stable orbits and send them on trajectories that intersect with Earth's path around the Sun. Jupiter is not simply a shield. It is a gravitational pump, capable of sending material both outward and inward, and the balance between its protective and its destructive effects on Earth depends on the specific configuration of orbits in a given era of solar system history. More troublingly, simulations of the early solar system suggest that Jupiter may have been directly responsible for some of the most catastrophic events in Earth's geological history. The Nice model, a theoretical framework developed in the early 2000s to explain certain features of the outer solar system, proposes that approximately 4 billion years ago, Jupiter and Saturn entered a gravitational resonance that destabilized the orbits of Uranus and Neptune, causing those two planets to migrate outward to their current positions. This migration sent an enormous wave of comets and asteroids cascading through the inner solar system, an event called the Late Heavy Bombardment, recorded in the crater record of the Moon and Mars as a period of intense impact activity lasting tens of millions of years. The Late Heavy Bombardment may have reset the conditions for life on Earth multiple times during that period, sterilizing the surface with impacts energetic enough to vaporize the oceans and melt the crust. Life that existed before the bombardment may have been extinguished, or it may have survived in deep ocean refugia, in hydrothermal systems, in places where the energy of impacts could not reach. The evidence in Earth's geological record is ambiguous, because Earth's own geological processes have erased most of the physical record from that era. But if the Nice model is correct, and it remains a model, not a confirmed history, with ongoing debates about its details, then Jupiter is responsible for an event that may have been the single most destructive episode in Earth's biological history. The same planet that may have shielded Earth from countless subsequent impacts also, in a previous era, may have launched the most devastating bombardment in Earth's geological record. This is not a simple story of Jupiter as protector or Jupiter as destroyer. It is a story of Jupiter as a gravitational force, operating on timescales and spatial scales so much larger than anything in human experience that the usual categories of helpful and harmful simply do not apply. Jupiter does what the mathematics of gravity and orbital dynamics dictates. Whether the consequences for Earth are beneficial or catastrophic in any given era depends on the specific configuration of solar system orbits at that moment in time, a configuration that itself changes on timescales of millions to hundreds of millions of years in ways that are only partially understood. What we know with confidence is that Jupiter's gravitational influence has shaped the architecture of the entire solar system. The asteroid belt exists in the form it does because Jupiter's gravity cleared out material from that region and established a resonance structure that gives the belt its current population distribution. The outer solar system's arrangement of ice giants and trans-Neptunian objects reflects billions of years of gravitational sculpting by Jupiter and Saturn acting in concert. Earth's orbit has been subtly influenced by Jupiter's gravity throughout its history. The delivery of water to early Earth, still a matter of active scientific debate, may have involved comets or asteroids whose orbits were perturbed by Jupiter in ways that sent water-bearing material into the inner solar system at the right time. Jupiter did not just form in the solar system. Jupiter participated in building it, in shaping it, in determining what kinds of objects ended up where. We exist in a solar system that Jupiter's gravity helped design. The layout of everything, the rocky inner planets, the asteroid belt, the ice giants, the Kuiper belt, the Oort cloud, reflects 4.5 billion years of Jupiter's gravitational fingerprint. This scale of influence is difficult to hold in mind because Jupiter looks from Earth like a point of light. A bright point, the brightest object in the night sky after Venus and the Moon, but still just a point. Our intuition about influence scales with distance. Things far away seem less relevant. Jupiter's gravitational influence scales with mass, not with how it looks to us. Its mass makes it relevant everywhere in the solar system simultaneously, operating quietly and continuously on everything from the largest planets to the smallest dust grains, pulling and perturbing and redirecting on timescales that span the entire history of the solar system. Go deeper into Jupiter. Not physically, because nothing survives going physically deeper than a few hundred kilometers below the cloud tops, but conceptually, following the physics downward through the atmospheric layers into the regions where temperatures and pressures exceed anything on Earth's surface. At the cloud tops, the temperature is roughly minus 145 degrees Celsius. Cold. Bitterly cold. The ammonia ice clouds that form the visible surface reflect sunlight efficiently, keeping the top of the atmosphere cold, even though Jupiter generates substantial internal heat. As you descend from the cloud tops, temperature and pressure both increase. Below the ammonia cloud layer, there is a layer of ammonium hydrosulfide clouds, a chemical that does not form clouds anywhere in Earth's atmosphere. Below that, at pressures of several times Earth's surface atmospheric pressure and temperatures above 0 Celsius, there are water clouds, ordinary water ice and water droplets, similar in some ways to the clouds you see from an airplane window on Earth, but embedded in an atmosphere of hydrogen and helium and existing under conditions that would be immediately lethal to any unprotected human being. Keep descending. The pressure continues rising. The temperature continues rising. At a pressure of roughly 1 bar, the same as Earth's surface atmospheric pressure, the temperature is already above 0 Celsius, comparable to a mild Earth day, but in an atmosphere that contains no oxygen only hydrogen and helium, and traces of every volatile chemical compound in the solar system. At 10 bars of pressure, what you would experience at a depth of roughly 100 meters below Earth's ocean surface, the temperature is around 70 Celsius. Hot enough to boil water at normal Earth pressures, though here the pressure is so high that water remains liquid. At 100 bars, the temperature exceeds 200 Celsius. The Galileo probe, descending on its parachute in 1995, reached a depth corresponding to about 22 bars of pressure before the thermal protection system reached its limits. The probe was destroyed at roughly 22 times Earth's surface pressure and temperatures around 150 Celsius. It had been descending for just under an hour. In that hour, it had travelled only a tiny fraction of the way through Jupiter's atmosphere, perhaps a few hundred kilometres, into an atmosphere that extends tens of thousands of kilometres before transitioning to metallic hydrogen. Below the depth where the Galileo probe was destroyed, things become genuinely alien. The distinction between gas and liquid disappears. Jupiter's hydrogen does not transition from gas to liquid at a sharp boundary the way water does when it freezes. Instead, it becomes gradually denser and more liquid-like over a range of pressures and temperatures. The atmosphere deepens into an ocean, not of water, but of liquid hydrogen, without a sharp phase boundary marking where one ends and the other begins. At a depth corresponding to pressures of around 1 to 2 million times Earth's surface atmospheric pressure, roughly 20,000 kilometers below the cloud tops, the hydrogen transitions to the metallic phase. The electrons detach from individual hydrogen atoms and flow freely through the material. The interior of Jupiter below that depth is an ocean of metallic hydrogen surrounding a core of heavier material, rock, ice, and potentially exotic forms of matter compressed to densities that have no analogue in any material on Earth's surface. What is Jupiter's core actually made of? This is not fully known. The most basic question about the interior of the largest planet in the solar system does not have a definitive answer. Juno's gravity measurements have provided constraints. The gravitational field of a planet encodes information about how mass is distributed inside it, and Juno's precise orbital measurements have allowed scientists to model Jupiter's interior structure with unprecedented accuracy. What those models suggest is that Jupiter does not have a sharp, compact, rocky core, the way early models predicted. Instead, the heavy elements seem to be distributed throughout a large fraction of the planet's interior, what scientists call a fuzzy core, a diffuse enrichment of heavy elements spanning a significant fraction of Jupiter's radius, rather than a compact nugget at the centre. One interpretation of this fuzzy core is that Jupiter's original rocky, icy core, the seed around which the hydrogen envelope accumulated during the planet's formation, was disrupted and partially dissolved by giant impacts during the early solar system's violent period of planetary formation. Another interpretation is that the core material simply diffuses outward over billions of years at the extreme pressures and temperatures of Jupiter's deep interior. Either way, the picture of Jupiter's interior that Juno's data suggests is fundamentally different from the simple models that dominated planetary science for decades. This is what makes Jupiter endlessly strange as a scientific object. The more precisely we measure it, the more it confounds simple models. Every spacecraft that has visited it, Pioneer 10 and 11, Voyager 1 and 2, Ulysses, Cassini during its gravity assist flyby, New Horizons during its flyby, Galileo during its extended orbital mission, and now Juno in its ongoing detailed survey, has returned data that required revision of existing models. Not small revisions, not tweaks at the edges, revisions to fundamental assumptions about how large planets form, how their atmospheres work, how their magnetic fields are generated, how they interact with their moons and with the broader solar system. The polar cyclones in geometric formations that Juno discovered were not in any model. The deep extent of the Great Red Spot was not predicted. The fuzzy core structure contradicts the standard formation models. The magnetic field's detailed structure, which Juno mapped with unprecedented precision, shows features that existing dynamo theory does not fully explain, including regions where the field is locally much stronger or weaker than the global average, in ways that suggest complex flows within the metallic hydrogen layer that are not captured by simple models of planetary dynamos. Every time we look more carefully, Jupiter is stranger than the previous look suggested. There is something almost philosophically instructive about this. Jupiter is the largest, most massive, most gravitationally dominant planet in the solar system. It has been observed by human eyes for millennia. Ancient Chinese, Babylonian, and Greek astronomers all documented its motion across the sky. Galileo discovered its 4 largest moons in 1610, making it the first system of bodies observed to orbit something other than Earth, providing direct observational evidence that not everything in the universe revolved around our planet. Jupiter has been studied by professional astronomers with telescopes for over 400 years. Spacecraft have visited it continuously since 1973, and we still do not fully understand it. We still do not know with certainty what its core is made of, or exactly how its magnetic field is generated, or why its polar cyclones arrange themselves in geometric patterns, or how the Great Red Spot has maintained itself for centuries, or whether its moons harbour life, or precisely how its gravity shaped the early solar system. 400 years of telescopic observation, 50 years of spacecraft visits, the most studied planet in the solar system after Earth, and Jupiter keeps returning data that does not fit our models. This is not a failure of science. It is the point of science. It is what exploration means when done honestly, not the confirmation of things already known, but the discovery of things that could not have been anticipated. Jupiter is large enough, complex enough, and strange enough that it continues to have things to teach us that we could not have predicted we needed to learn. The spacecraft we have sent there have done something that has no historical parallel in human experience. They have allowed us to move from seeing Jupiter as a point of light to understanding it as a system, as a world, as something with physical reality extending deep into a structure that our instruments can probe and our physics can attempt to describe. That transition from point of light to measurable physical system is one of the genuine intellectual achievements of the space age, and it is still ongoing. Juno is still there, still orbiting, still absorbing radiation in its titanium vault, still sending data across the 800 million kilometers between Jupiter and Earth, a journey that takes roughly 44 minutes at the speed of light, meaning that when a Juno data transmission arrives at the Deep Space Network antenna in Goldstone or Madrid or Canberra, it carries information about conditions that existed nearly an hour earlier, when the spacecraft was on a different part of its orbit, above a different region of Jupiter's atmosphere, measuring a different slice of a planet that changes continuously and faster than any other planet in the solar system. The Europa Clipper is now in transit toward Jupiter. It launched in October 2024 and will arrive in the Jovian system in 2030. When it arrives, it will begin a series of close flybys of Europa, nearly 50 flybys over roughly 4 years, each one returning detailed measurements of the ice shell, the ocean beneath, the surface chemistry, the plumes if they are real and detectable, the magnetic environment, and the radiation exposure that any future lander or subsurface probe would need to withstand. After the Clipper, the European Space Agency's JUICE mission, Jupiter Icy Moons Explorer, is also en route to the Jupiter system, arriving in 2031 and spending several years studying Ganymede, Callisto and Europa before eventually entering orbit around Ganymede, the first spacecraft ever to orbit a moon other than Earth's moon. 2 spacecraft from 2 different space agencies converging on Jupiter and its moons in the early 2030s. One focused on Europa's potential habitability, one on the broader system of icy moons and what they reveal about the conditions for ocean worlds throughout the solar system and throughout the universe. The questions those missions will attempt to answer are among the most significant in all of science. Whether Europa's ocean is habitable, whether there are signs of biological activity, however subtle, in the chemistry of its surface or its plumes, whether Ganymede's internal ocean, yes, Ganymede also has a subsurface ocean confirmed by magnetic field measurements, could also harbour life, whether the conditions that make Europa potentially habitable are common or rare among the ice-covered ocean worlds that appear to be abundant throughout the outer solar system and, by extension, throughout planetary systems around other stars. These questions connect Jupiter to the broadest questions in astrobiology. The discovery that liquid water can exist beneath the ice shells of moons far from the Sun, maintained not by sunlight but by tidal heating from a massive planetary host, dramatically expanded the range of environments where life might be possible in the universe. Before Europa, the habitable zone around a star was defined as the range of distances where liquid water could exist on a planetary surface, given the star's luminosity. Europa demonstrated that tidal heating can maintain liquid water far outside that zone. Every giant planet with large moons is potentially a system that contains ocean worlds. Giant planets are common around other stars. Their moons are probably common too, though we cannot yet detect them directly. Jupiter may therefore be pointing toward a general principle, that the solar system, and by extension other planetary systems, contain far more potential environments for liquid water, and therefore far more potential environments for life than the simple habitable zone model suggested. The scariest planet in the solar system, with its lethal radiation and crushing pressures and centuries-long storms and metallic hydrogen interior, may also be the key to understanding how common life is in the universe. That is a strange thing to contemplate, that the planet most hostile to life as we know it, the planet that would kill a human being at its outer edges before they could register what was happening, is also potentially the custodian of more liquid water than exists in all of Earth's oceans, and is pointing us toward a principle that could mean life is far more widespread in the universe than we had any reason to suspect before we looked closely enough. Jupiter does not care about this irony. It continues to rotate, slightly faster than 10 hours per revolution, its bands counter-rotating, its polar cyclones maintaining their geometric formations, its volcanic moon continuously resurfacing itself while feeding plasma into the radiation belts, its ocean moon quietly keeping its liquid water in the dark beneath kilometers of ice that has never seen sunlight and may never need to. It has been doing this for 4.5 billion years. It will continue doing it for billions more. The Sun will eventually exhaust its hydrogen fuel and expand into a red giant, engulfing the inner planets and dramatically altering the solar system's architecture. What happens to Jupiter when the Sun expands is one of the more genuinely uncertain questions in long-term solar system evolution. Models suggest Jupiter may migrate outward as the Sun loses mass, or its orbit may be perturbed by the dynamics of the red giant phase. What happens to Europa's ocean when the Sun's luminosity increases during its red giant phase is an interesting calculation. The additional energy input might melt the ice shell entirely, exposing the ocean to space before the ocean itself eventually boils away. But that is billions of years from now. On any timescale relevant to human existence or human civilization or even human species survival, Jupiter will remain approximately where it is, doing approximately what it does, maintaining its magnetic field and its radiation belts and its volcanic moon and its ocean moon and its geometric polar cyclones and its ancient storm, all simultaneously, all continuously, all at scales that dwarf anything on the planet where all of human history has occurred. We have been watching it for thousands of years from a distance at which it looked like a light. We have been studying it with spacecraft for 50 years, and it keeps returning data that does not fit our models. We have sent a probe inside its atmosphere, and it was destroyed in an hour. We are sending more spacecraft now, and they will tell us things we cannot currently predict because Jupiter has consistently demonstrated that it contains more complexity, more strange physics, more unexpected phenomena than any model built before the measurements could anticipate. The planet that looks peaceful from here, the beautiful banded oval with its famous red eye, the brightest star-like object in the night sky on most nights, is running a nuclear-scale radiation environment, maintaining a magnetic field 20,000 times stronger than Earth's, hosting the most volcanically active body in the solar system, potentially sheltering more liquid water than all of Earth's oceans combined, and operating weather systems that have been running continuously for longer than any human civilization has existed, powered partly by heat left over from the formation of the solar system itself. That gap between what it looks like and what it is one of the largest gaps between appearance and reality that you will encounter in the natural world. It is what makes Jupiter endlessly strange. It is what makes it endlessly worth studying. And it is why every measurement, every flyby, every probe, every orbit of every spacecraft we have ever sent there has returned data that required us to revise what we thought we knew and look more carefully at what is actually there. What is actually there is more violent, more complex, more strange, and more consequential for everything in this solar system, including the planet you are on right now, than it looks. It never looked peaceful to anything that got close enough to see it clearly. There is a number that planetary scientists use when they want to convey the scale of Jupiter's gravitational dominance over the solar system, and it is a number that tends to stop conversations for a moment when people hear it for the first time. Jupiter contains approximately 2.5 times more mass than all other planets in the solar system combined. Not more than any individual planet, more than all of them together. Saturn, Uranus, Neptune, Earth, Venus, Mars, Mercury. Add up every gram of every other planet orbiting the Sun, and you still only reach about 40% of Jupiter's mass. The solar system, in terms of mass distribution, is essentially the Sun and Jupiter, with everything else, including the planet you are standing on, being a relatively minor footnote in the inventory. This mass dominance has consequences that extend far beyond what most people think about when they consider Jupiter's role in the solar system. One of the most counterintuitive consequences involves the Sun itself. Jupiter's gravity pulls on the Sun. This is not a subtle effect. Every body with mass pulls on every other body with mass. Newton's law of universal gravitation applies symmetrically, which means that just as the Sun's gravity holds Jupiter in its orbit, Jupiter's gravity tugs on the Sun. The Sun is so much more massive than Jupiter that this tug produces only a small displacement. The Sun does not orbit Jupiter, obviously, but the displacement is real and measurable. The Sun does not sit perfectly stationary at the center of the solar system. It wobbles. It traces a small orbit around the solar system's common center of mass, the barycenter, in response to Jupiter's gravitational pull. The barycenter of the Jupiter-Sun system sits at approximately 1 solar radius from the Sun's center, which means it is just barely outside the Sun's surface. The Sun traces a small ellipse around this point with a period of roughly 12 years, matching Jupiter's orbital period. The amplitude of this wobble, the displacement of the Sun's center from the barycenter, is approximately 740,000 kilometers. 740,000 kilometers is roughly 1 solar radius. The Sun is wobbling back and forth by a distance equal to its own radius, driven primarily by Jupiter's gravity on a 12-year cycle. This matters for a reason that connects Jupiter directly to the search for planets around other stars. The primary method by which astronomers have detected most of the thousands of exoplanets discovered in the past 3 decades is called the radial velocity method, sometimes called the Doppler method. It works by detecting the slight wobble that a planet induces in its host star, the same wobble that Jupiter induces in our Sun, by measuring tiny Doppler shifts in the star's light as it moves toward and away from Earth. When a massive planet orbits a star, the star's light is very slightly blue-shifted when the star is moving toward us, and very slightly red-shifted when the star is moving away. Detecting these shifts requires instruments of extraordinary precision, but they can be detected. The first exoplanet discovered around a Sun-like star, 51 Pegasi b, detected in 1995, was found using precisely this method. It was a Jupiter-mass planet orbiting its star far closer than Mercury orbits the Sun, producing a radial velocity signal large enough to be detected with the instruments of the era. Jupiter-sized planets in close orbits produce the strongest signals and were therefore the first to be detected. The catalogue of known exoplanets is therefore biased toward Jupiter-like objects, particularly those in close orbits, because those are the ones most easily detectable with current methods. This means that our understanding of other planetary systems has been shaped significantly by what is easiest to find. And what is easiest to find are planets similar to Jupiter. Whether Jupiter-like planets, massive gas giants orbiting at various distances from their host stars, are common throughout the galaxy is a question with significant implications for the frequency of habitable planetary systems like ours. Some planetary system architectures produce stable orbits for rocky inner planets. Others, particularly those where a Jupiter-mass planet migrated inward through the inner solar system during its formation, may have disrupted or destroyed any rocky planets that might otherwise have formed there. The migration of Jupiter itself during the early solar system is a topic of active and sometimes contentious scientific debate. The Grand Tack hypothesis, one of the more dramatic proposed scenarios for early solar system evolution, suggests that Jupiter formed at roughly 3 to 4 astronomical units from the Sun, then migrated inward toward the Sun, reaching as close as 1.5 astronomical units inside the current orbit of Mars, before Saturn's gravity halted the inward migration and caused both planets to migrate back outward to roughly their current positions. If this happened, and the evidence is circumstantial but taken seriously by many planetary scientists, then the early inner solar system was dramatically disrupted by Jupiter's passage through it. Material that might have formed a larger Mars or additional rocky planets was swept up, scattered, or ejected. The asteroid belt was cleared of much of its original mass. The architecture of the inner solar system, the specific sizes and orbital properties of the rocky planets, reflects this disruption. Mars is smaller than models of planetary formation predict it should be, and one explanation is that Jupiter's inward migration starved the Mars-forming region of material before the migration reversed. If the grand tack is correct, Earth owes its current form, the specific mass, the specific orbit, the specific water content, to a complex dynamical dance between Jupiter and Saturn that played out in the first few million years of solar system history. Slightly different initial conditions, slightly different migration dynamics, and the planet at Earth's position might have been smaller, or larger, or drier, or might not have existed at all. The water on Earth is itself connected to Jupiter in ways that are still being worked out. The rocky inner solar system, the region where Earth formed, is in principle too hot during planetary formation for water ice to survive. Earth's water should not be here. The standard explanation is that water was delivered to early Earth by impactors, asteroids or comets that formed in cooler outer regions of the solar system and were subsequently scattered into Earth-crossing orbits. The mechanism that scattered them into Earth-crossing orbits involves gravitational perturbations from Jupiter and Saturn. Jupiter, in other words, may be responsible for delivering the water that covers 70% of Earth's surface, and that is a prerequisite for every form of life on this planet. This is the scale at which Jupiter operates. Not just a large planet in the outer solar system, not just a planet with impressive storms and dangerous radiation, but a gravitational architect whose influence pervades the entire history of the solar system, from its formation to the present day, and whose effects on Earth specifically include the delivery of the water that makes the planet habitable, and possibly the bombardment events that repeatedly threatened to sterilize it. The same gravitational influence that may have delivered water to Earth also periodically sends asteroid-sized objects from the main belt into Earth-crossing orbits. The mechanism involves orbital resonances, regions of the asteroid belt where the orbital period of an asteroid stands in a simple ratio to Jupiter's orbital period. An asteroid at a 2-to-1 resonance with Jupiter completes exactly 2 orbits for every 1 Jupiter orbit, which means it receives a gravitational kick from Jupiter at the same point in its orbit every time. These repeated kicks accumulate, gradually increasing the asteroid's orbital eccentricity until the orbit crosses the path of one of the inner planets. The Kirkwood gaps, regions in the asteroid belt that are nearly devoid of asteroids, correspond precisely to the major resonances with Jupiter. The 3-to-1 resonance, the 5-to-2 resonance, the 7-to-3 resonance, the 2-to-1 resonance. At each of these locations in the asteroid belt there is a gap, cleared by Jupiter's gravitational influence over billions of years. Asteroids that drift into these resonance zones have their orbits destabilized and are eventually either ejected from the solar system entirely or sent into the inner solar system on orbits that may intersect with Earth, Mars, or Venus. The asteroids that produced the largest impact craters on Earth, the impacts responsible for mass extinction events in Earth's biological history, may have been delivered from the asteroid belt through exactly this mechanism. Jupiter's gravity, operating over millions of years on the orbital dynamics of the asteroid belt, periodically sends city-sized rocks on trajectories that intersect with Earth's path. The Chicxulub impactor, the asteroid or comet fragment whose impact 66 million years ago triggered the mass extinction that killed the non-avian dinosaurs, may owe its Earth-crossing trajectory to a gravitational resonance with Jupiter that destabilized its orbit millions of years before the impact. The connection between Jupiter's gravity and the mass extinction events that have punctuated Earth's biological history is not simple or direct. It is a probabilistic influence operating over geological timescales, increasing the rate at which dangerous impactors reach Earth-crossing orbits, without determining any specific impact event. But the statistical influence is real. Jupiter shapes the impactor flux experienced by Earth. It always has. It will continue to do so for as long as Jupiter exists and the asteroid belt continues to contain material. What this means for the long-term future of life on Earth is something that planetary scientists and astrobiologists think about with a mixture of fascination and discomfort. The major mass extinction events in Earth's history, the end Ordovician, the late Devonian, the end Permian, the end Triassic, the end Cretaceous, each eliminated a substantial fraction of all species on Earth. The end Permian event, roughly 252 million years ago, eliminated approximately 96% of all marine species and 70% of all terrestrial vertebrate species. It is the largest mass extinction in Earth's geological record, and its causes are still debated, with volcanic eruptions and potentially impact events both implicated. After each mass extinction, the surviving lineages radiated into the ecological niches vacated by the extinct species, producing new forms of life, new body plans, new ecological relationships. The mass extinctions were catastrophic for the species they eliminated, but were, in some sense, creative for the biosphere as a whole. They opened ecological space that drove evolutionary innovation. The mammals that eventually gave rise to humans are only here because the non-avian dinosaurs were eliminated in the end Cretaceous extinction, freeing ecological niches that small Mesozoic mammals subsequently expanded into. If Jupiter's gravitational influence was a contributing factor to any of the mass extinctions that shaped Earth's biological history, then Jupiter is, in some indirect sense, part of the causal chain that led to the existence of human beings. The same gravitational force that sent the Chicxulub impactor into an Earth-crossing orbit also, through the extinction of the dinosaurs, created the conditions in which mammalian evolution could proceed in the direction that produced primates and eventually Homo sapiens. This is not how Jupiter intends it. Jupiter has no intentions. It is a ball of hydrogen and helium with a magnetic field and a storm, operating according to the laws of physics with complete indifference to the biological consequences on a small, rocky planet 800 million kilometers away. But the consequences are there, embedded in Earth's geological and biological record, connecting the largest planet in the solar system to the deepest questions about why life on Earth has taken the specific forms it has taken. Look at Jupiter differently for a moment, not as a threat, not as an influence, not as a gravitational architect, but as a laboratory, as a naturally occurring experiment in planetary physics operating under conditions that cannot be recreated anywhere on Earth, and that cannot be studied except from the distance of a spacecraft or a telescope. The physics happening inside Jupiter's metallic hydrogen layer is relevant to physics experiments that human beings are attempting to conduct in laboratories on Earth. High-pressure physics, the study of how matter behaves under extreme compression, is an active field of research with applications ranging from materials science to fusion energy. The conditions inside Jupiter provide a natural laboratory for pressures and temperatures that terrestrial experiments can only begin to approach. Studying Jupiter's interior through its gravitational field, its magnetic field, and its atmospheric dynamics provides constraints on the physics of matter under conditions that no Earth laboratory can replicate. The dynamo process that generates Jupiter's magnetic field, the conversion of kinetic energy in flowing metallic hydrogen into magnetic field energy through electromagnetic induction, is a version of the same process that generates Earth's magnetic field in its liquid iron outer core. Earth's dynamo is more accessible to study because the planet is smaller and the core is closer to the surface. But it is also more complex in its chemistry because iron behaves very differently from hydrogen under pressure. Jupiter's hydrogen dynamo is in some ways a cleaner system for studying the fundamental physics of planetary magnetic field generation. What Juno learns about Jupiter's dynamo has direct implications for understanding how Earth's magnetic field works and how it might change in the future. Jupiter's atmospheric dynamics, the counter-rotating jet streams, the vortex formation, the turbulent cascades between scales, are a natural experiment in fluid dynamics at Reynolds numbers and Rossby numbers that no wind tunnel or computer simulation can fully capture. The Great Red Spot is a vortex that has maintained itself for centuries in a turbulent fluid environment that should, according to simple models, cause it to dissipate on much shorter timescales. Understanding how it persists is a problem in fluid dynamics with implications for understanding long-lived vortex structures in atmospheres and oceans throughout the solar system and on exoplanets. The atmospheric chemistry of Jupiter, the complex organic molecules forming in its upper atmosphere, the photochemical reactions driven by ultraviolet sunlight, the possible synthesis of amino acid precursors in its lightning-rich cloud layers, is relevant to the chemistry of the early Earth and to the broader question of how complex organic chemistry arises in planetary atmospheres. Carl Sagan and others proposed in the 1970s that Jupiter's atmosphere might be a natural synthesis chamber for organic molecules, potentially including the building blocks of life. Whether life-relevant chemistry is actually happening in Jupiter's atmosphere is unknown, and would require analysis far more detailed than anything current spacecraft can provide. But the proposal is chemically reasonable and has never been definitively ruled out. This is one of the stranger ideas in planetary science, that Jupiter, the most hostile environment in the solar system for life as we know it, might simultaneously be a natural laboratory for the prebiotic chemistry that could lead to life. The same atmospheric chemistry that makes Jupiter's upper cloud layers cold and toxic and irradiated might also be continuously synthesizing complex organic molecules that rain downward into deeper, warmer, higher pressure layers where different chemistry becomes possible. No one has seriously proposed that life exists in Jupiter's atmosphere. The dynamical timescales are too short. Any organic chemistry would be rapidly transported into pressure and temperature regimes that destroy it before it could accumulate or self-organize. But the chemistry itself, the synthesis of complex organics in a hydrogen-dominated atmosphere rich in lightning and UV irradiation, is a process that may have relevance to the chemistry of the early Earth's atmosphere and to the chemistry of other planetary atmospheres throughout the galaxy. Jupiter is therefore simultaneously a record of the early solar system, a gravitational architect of the current solar system, a potential host of extraterrestrial life in its moon system, a laboratory for extreme physics and atmospheric dynamics, and a natural experiment in prebiotic chemistry. It is the most scientifically consequential object in the solar system after the Sun, and it has been consistently demonstrating over 50 years of spacecraft exploration that every model built to describe it underestimates its complexity. The next major revelation about Jupiter is almost certainly coming from the Europa Clipper. When the spacecraft arrives in 2030 and begins its series of Europa flybys, it will be carrying instruments designed to detect the specific chemical signatures of habitability, the presence of liquid water, the chemistry of organic compounds on the surface, the salinity and pH of the ocean, if it can be inferred from surface deposits, the thickness and dynamics of the ice shell, the presence and composition of plumes, if they exist. The measurements will not answer the question of whether life exists in Europa's ocean, but they will narrow the range of possibility in ways that will determine the priority and design of the next generation of missions. If the Clipper finds that Europa's ocean has the right chemistry, liquid water, appropriate salinity, chemical energy available, organic molecules present, the scientific pressure to send a lander and eventually a subsurface probe through the ice will become enormous. The engineering challenges of landing on Europa, surviving its radiation environment long enough to conduct meaningful science, and eventually melting or drilling through kilometers of ice to sample the ocean are substantial. But they are not obviously impossible. They are engineering challenges of the same general character as the challenges that have been solved by previous planetary exploration missions, just significantly harder. A probe in Europa's ocean would be the most significant event in the history of astrobiology. Not because it would necessarily find life. It might find a sterile ocean, which would itself be scientifically important, but because directly sampling a potentially habitable ocean on another world would represent the first time in human history that we had direct access to an extraterrestrial environment where the conditions for life are met. The measurement of whether life is present or absent in that environment would provide the first real data point for the question of how common life is in the universe. Currently, that question has exactly one data point: Earth, one inhabited planet. No way to determine from a single data point whether life is common or rare. Every proposed astrobiological environment, Mars, Europa, Enceladus, Titan, is a potential second data point. Finding life in any of them would demonstrate that life arises wherever conditions allow. Finding no life in all of them would not definitively demonstrate that life is rare, but it would narrow the range of environments we consider habitable, and would shift the statistical inference toward rarity. Jupiter is the host of the most accessible and most compelling of these potential second data points. Europa is close enough, large enough, and well characterized enough that missions to it are being funded and built right now. The ocean is almost certainly there. Whether anything lives in it is the question that may be answered within the lifetimes of people alive today. Not certainly, not soon, but possibly. On the timescale of the next few decades, if the Clipper's findings are sufficiently compelling, and if the political and funding environment supports a follow-on mission, we could have direct measurements from within an extraterrestrial ocean. That possibility, distant but real, is one reason Jupiter occupies a unique position in the scientific imagination. It is not just the largest planet, or the most dangerous environment, or the most gravitationally influential object in the solar system. It is the doorway to the most important unanswered question in all of science: whether we are alone, whether life arises wherever conditions allow, or whether Earth is a singular exception in a universe that is otherwise sterile. Jupiter does not know it is a doorway. It does not know anything. It is hydrogen and helium and metallic phases and magnetic fields and storms. It has been rotating for 4.5 billion years, and it will continue rotating long after the spacecraft we send to study it have fallen silent and drifted out of orbit, or burned up in its atmosphere. It has seen the formation of Earth, the emergence of life, the evolution of everything that has ever lived on this planet, the entire span of human history, the entire development of science and technology, and the capacity to ask questions about the universe, all of it, while rotating slightly faster than 10 hours per revolution, maintaining its bands and its storms and its radiation belts with complete indifference. The indifference is part of what makes it strange to contemplate. Jupiter is enormous and powerful and consequential, and it does not care. It is not malevolent. It is not protective. It is not anything except a physical system obeying the laws of physics. The fact that those laws, applied at Jupiter's mass and in Jupiter's position in the solar system, have produced consequences both catastrophic and potentially life-enabling for a small rocky planet 800 million kilometers away, that is not Jupiter's intention. It is the mathematics of gravity and orbital dynamics and atmospheric physics, operating without purpose or preference, producing outcomes that matter enormously to the organisms on Earth who have developed the capacity to notice them. There is something clarifying about that. Jupiter is not a metaphor. It is not a symbol. It is a physical object, and its relationship to Earth is entirely mediated through physical forces, gravity, radiation, tidal forces, that operate according to equations that have no room for intention or meaning. And yet the consequences of those equations for the history of life on Earth are so profound and so interwoven with every aspect of that history that it is almost impossible to understand what Earth is and what life on Earth has been without accounting for Jupiter's influence. The solar system is not a collection of independent planets, each doing its own thing. It is a dynamical system in which every component is coupled to every other component through gravity, and the most massive component, the one that dominates the dynamical behavior of everything except the Sun, is Jupiter. To understand Earth, you have to understand Jupiter. To understand the history of life, you have to understand the impacts that punctuated it and the gravitational source of the impactors. To understand the water in Earth's oceans, you have to understand the dynamics that delivered it. To understand the architecture of the inner solar system, you have to understand Jupiter's migration history. And to understand any of that, you have to get close enough to measure it, which means sending spacecraft into one of the most hostile radiation environments in the solar system, protecting their instruments in titanium vaults, watching them absorb the equivalent of hundreds of millions of dental X-rays over years of operation, and extracting from the data they return a picture of physical processes operating at scales and in regimes that have no analogy in human experience. That is what planetary science at Jupiter has required. That is what it continues to require. That is what the Europa Clipper will require, and whatever comes after the Clipper will require. The planet that looks like a peaceful banded oval from Earth is actually a radiation environment, a gravitational engine, a chemical laboratory, a record of solar system formation, a potential host of extraterrestrial life, and the dominant dynamical influence on everything in the solar system, except the Sun. It has been all of these things simultaneously for 4.5 billion years. We have known about it for millennia and understood it for decades, and we still do not fully understand it. Every new measurement reveals something the previous model did not predict. Every spacecraft returns data that requires revision of established theory. Every close look at Jupiter produces the same result, that it is stranger, more complex, more consequential, and more scientifically rich than the look before suggested. That is what Jupiter is. That is why it matters. That is why it is worth sending spacecraft into lethal radiation environments to study, worth building instruments of extraordinary sensitivity to measure its gravitational field and its magnetic field and its atmospheric chemistry, worth the decades of work and billions of dollars and thousands of scientists and engineers who have dedicated careers to understanding a planet that most people on Earth have seen only as a bright point of light in the night sky. The point of light is a lie, a beautiful, peaceful, utterly misleading lie. What is actually there, what has always been there, operating at scales and in regimes entirely beyond human intuition, is one of the most extraordinary physical systems in the known universe, sitting 800 million kilometers away, visible to the naked eye, and almost entirely misrepresented by its own appearance. And yet, we keep looking at it. Every clear night, in every city, on every continent, someone points a backyard telescope at that bright point of light and watches the bands shift slowly across the disk, and sees the 4 moons arranged in a line, and feels something that is difficult to name precisely. Not fear, not awe exactly, something quieter than both. The feeling of looking at something that is genuinely beyond you. Not beyond your intelligence or your curiosity, but beyond your scale. Beyond the scale of anything your nervous system evolved to process. Jupiter does not fit inside human intuition. It never has. You can learn the numbers: 1,300 Earths by volume, 20,000 times Earth's magnetic field strength, winds of 500 kilometers per hour as background conditions, a storm older than every nation on Earth. And the numbers are accurate, and the numbers are meaningful, and the numbers still do not produce the actual feeling of the scale. The scale exceeds what numbers can deliver to the part of the brain that processes reality rather than arithmetic. What we have learned about Jupiter over 50 years of spacecraft exploration is not just a collection of facts about a large planet. It is a lesson about the difference between the universe as it appears and the universe as it is. Jupiter looks like one thing and is another thing entirely. The appearance is accessible. The reality requires instruments, mathematics, decades of patient measurement, and a willingness to revise what you thought you knew every time new data arrives. That lesson applies everywhere, not just to Jupiter, to every object we look at from a distance and think we understand because we can see it. The universe is consistently, reliably, almost comically more complex than it looks. Jupiter is just the most dramatic local example, the case where the gap between appearance and reality is large enough and close enough that we can actually measure it, probe it, send spacecraft into it, and come back with data that demonstrates exactly how wrong the peaceful-looking surface was. We live in a solar system dominated by an object we barely understand, an object that helped build the planet we live on, delivered the water we drink, shaped the impacts that drove the evolution of every living thing, including us, and maybe sheltering an ocean that contains more liquid water than all of Earth's seas, an ocean that has been sitting there in the dark for 4.5 billion years, waiting while everything that has ever lived on this planet lived and died and evolved and eventually produced creatures capable of wondering whether anything lives in that ocean. That is where we are. Looking outward at a planet that has always been more than it appeared, sending spacecraft that survive longer than anyone expected, asking questions whose answers will take decades to return, building instruments to detect chemistry in an ocean we have never touched, beneath ice we have never stood on, orbiting a planet that would kill us in hours if we got close enough to try. The universe does not make it easy. It never has. It puts the most important answers behind the most extreme barriers. The ocean that might answer the oldest question in science is beneath kilometers of ice inside a radiation environment that destroys spacecraft. The planet that holds the most clues to our own origin looks, from where we stand, like a light. But the light is there every night, and so is the question. And we are, for the first time in the 4.5 billion year history of this solar system, the kind of thing that can look at that light, understand what it actually is, and decide to go find out what it is hiding. That is not nothing. That might be everything. Think about what it took to get here. Not the spacecraft, not the engineering, the thinking. Somewhere around 400 years ago, a man in Italy pointed a crude tube of glass at a bright point in the night sky and saw 4 tiny dots arranged beside it. He watched them night after night and realized they were moving, not randomly, not following the stars, but orbiting something other than Earth. In a universe that every authority insisted revolved entirely around Earth, Galileo Galilei watched 4 moons circle Jupiter and understood, quietly and with complete certainty, that the authorities were wrong. He did not have spacecraft. He did not have radio telescopes or magnetometers or plasma wave instruments or titanium radiation vaults. He had a lens, a dark sky, and the willingness to believe what he was seeing rather than what he had been told. That willingness to look at the evidence and follow it wherever it leads, regardless of how inconvenient the destination, is the same willingness that sent Juno into Jupiter's radiation belts 4 centuries later. The instrument changed. The impulse did not. 400 years of looking. 400 years of gradually closing the gap between the point of light and the reality behind it. And we are still closing it. The gap is smaller than it was in Galileo's time, but it is not closed. It will not be closed by the Europa clipper. It will not be closed by whatever comes after the clipper. Jupiter has demonstrated with remarkable consistency across every mission ever sent to study it, that every time we look more carefully, we find more than the previous look revealed. There is no reason to believe that pattern will end with the next mission, or the one after that. This is not a frustrating conclusion. It is the most honest description of what science actually is. Not a march toward complete knowledge. Not an accumulation of answers that eventually fills in all the blanks, but a process of replacing large ignorances with smaller ones, of discovering that every answer opens onto a landscape of new questions that were not visible before the answer was found. Jupiter is a nearly inexhaustible source of new questions. Every measurement constrains something and reveals something unexpected. Every model revision exposes a new assumption that needs testing. The The scientists who will answer the questions currently on the table, whether Europa's ocean is habitable, how Jupiter's fuzzy core formed, why the polar cyclones arrange in geometric patterns, what maintains the great red spot against the turbulence that should destroy it, are in many cases already working. They are graduate students and postdoctoral researchers in planetary science departments right now, running simulations of Jupiter's interior on supercomputers, analysing Juno data, looking for patterns in the magnetic field structure, designing instruments for future missions, writing papers that will be read by the people who design the spacecraft that will eventually carry those instruments to Jupiter's moons. The people who will answer the questions that those answers reveal, the deeper questions that are not yet visible because they require the answers to current questions before they can even be formulated, those people may not be born yet. The history of Jupiter exploration is a multi-generational project. It began before the space age with telescopic observation, accelerated dramatically with the Pioneer and Voyager flybys of the 1970s, deepened with the Galileo orbital mission of the 1990s and 2000s, and is now in its Juno and Clipper phase. Each phase built on the last. Each generation of scientists inherited the questions opened by the previous generation and passed new ones to the next. This is how science operates on objects at Jupiter's scale of complexity. Not quickly, not neatly, not with the dramatic resolution of a mystery novel where the final chapter delivers a complete answer. Slowly, cumulatively, across careers and generations, each step building on the last, each answer creating the foundation for the next question. And embedded in all of it, in every measurement and every model and every mission, is the same basic impulse that Galileo had when he pointed his tube of glass at that bright point and decided to look carefully enough to see what was actually there. We are still doing that. We have better tubes now. We can send the tube to Jupiter rather than looking from Earth. We can build instruments that measure magnetic fields and plasma densities and gravitational harmonics and atmospheric chemistry. But the act is the same. The decision to look carefully, to trust the measurement over the assumption, to follow the evidence wherever it leads, that has not changed in 400 years. Jupiter has been there for all of it, rotating on its 10-hour cycle, maintaining its bands and its storms and its radiation belts, holding its ocean moon in its gravitational embrace, completely indifferent to the small creatures on the third planet who keep pointing things at it and being surprised by what they find. It will be there for whatever comes next. For the Clipper's flybys and the data they return, for the mission after the Clipper that those data will make necessary, for the generation of scientists not yet born who will design that mission and spend their careers analysing its results. Jupiter will still be rotating, still generating its magnetic field, still maintaining its polar cyclone formations in their geometric arrangements, still heating Io to volcanism and keeping Europa's ocean liquid in the dark. The ocean will still be there. Whatever is or is not in it will still be there, waiting with the patience of something that has no concept of waiting, that simply exists in the same state it has existed in for 4.5 billion years, indifferent to the question of whether anyone will ever come to ask. We are going to go ask, not because we know what the answer is, not because we are confident there is anything in that ocean to find, but because the question is real, and the ocean is real, and we have, for the first time in the history of this solar system, developed the capacity to approach it. That capacity is fragile. It depends on funding and political will and institutional continuity, and the decisions of many people who may or may not understand what is at stake. It is not guaranteed to be exercised. Humanity has had the capacity to return humans to the moon for decades and has not done so. Having the capacity and using it are different things. But the capacity exists, and the question exists. And somewhere between those two facts is a mission, maybe this decade, maybe the next, maybe the one after, that will lower an instrument through kilometers of ice and into an ocean that has never been touched by anything from outside its own world, and will measure whatever is there, and will transmit that measurement across 800 million kilometers at the speed of light, and the data will arrive at a receiver on Earth, and scientists will look at it and know something that no one has ever known before. What they will know is uncertain. What it will mean is uncertain. Whether it will reveal life, or sterility, or something in between, or something that does not fit either category neatly, uncertain. But the moment of measurement will be real. The data will be real. And whatever it shows, it will be the first time in 4.5 billion years that the question of whether that ocean contains anything has had an answer other than silence. Jupiter made that ocean. Jupiter's gravity heats Europa from the inside, keeps the water liquid, maintains the conditions that make the question worth asking. The most dangerous planet in the solar system built the most tantalizing potential home for extraterrestrial life in the solar system. The destroyer and the creator operating through the same mechanism. The same tidal force that tears Io apart gently warms Europa's interior. The same gravity that sends asteroids into Earth-crossing orbits keeps Europa in the resonance that maintains its tidal heating. The same magnetic field that would kill an unprotected human in hours is part of the same planetary system that may be sheltering an ocean. This is not irony, it is physics. It does not resolve into a lesson or a moral. It simply is what it is, a physical system of extraordinary complexity, producing consequences that span from lethal to life-enabling, depending on where you are standing and what you are made of. We are made of the right things, standing in the right place at what might be exactly the right moment. The moment when the question about that ocean has become answerable in principle and is becoming answerable in practice. That is an unusual position to be in. Most questions about the universe are not answerable in practice by the civilization that first formulates them. The question of whether Europa's ocean contains life has been formulable since the Galileo spacecraft returned its magnetic field measurements in the 1990s. For 30 years, it has been a real question with no practical path to an answer. Now there is a path. It is long and expensive and uncertain, but it exists. We live at a specific moment in the history of this solar system, the moment when a species on the third planet has developed just enough capability to begin asking real questions about the fourth largest moon of the fifth planet. 4.5 billion years of planetary evolution leading to this specific moment of capability meeting question. Whether we use it, whether the clipper leads to a lander, whether the lander leads to a probe, whether the probe reaches the ocean and measures what is in it, depends on choices that are being made now and will continue to be made by people who may or may not understand what is at stake. Jupiter does not care what they decide. It will keep rotating either way. But we should care, because the question is ours. The ocean is not going anywhere. The ice will still be there in 100 years. The tidal heating will continue for billions more. The opportunity is not time-sensitive on Jupiter's timescale. It is time-sensitive on ours. And that might be the most important thing Jupiter has to teach us. Not about planetary physics or atmospheric dynamics or magnetic field generation or the chemistry of metallic hydrogen. About us. About what it means to be the kind of thing that can formulate a question this large, develop the capacity to approach an answer, and then have to decide whether to actually go ask it. That decision is happening now, in funding committees and mission planning documents and congressional budget hearings and the career choices of graduate students deciding whether to spend their lives on problems whose answers they may not live to see. Jupiter is waiting. It has been waiting for 4.5 billion years without knowing it is waiting, and it will wait for billions more with the same indifference. The question is whether we will.